Africa, or perhaps a Minister of Finance, or maybe both, and asking you all, what is all this, all these posters, all these presentations, what relevance do they have for improving practice and improving policy in my country and in my district? I'm afraid you haven't got either of those people, you're stuck with me, but I'll try and represent them a little bit. I do find myself rather humbled by the sheer volume of science and experience that we're all surrounded by. And as I get older, I realise how little I know and how the little I know seems to get smaller every day. Many of the discussions that I've been having so far have reinforced that there are many things that we really don't understand about groundwater, and that makes it quite difficult in some cases to draw out the implications for practice and policy. But that's what I want to try and do, to make some links between the science of groundwater and practice and policy. Sometimes I talk about it as practice and policy in that order, and sometimes policy and practice. It's never quite clear which drives the other. But I'll give a little bit of background. I want to say something about the status of water supply, particularly in rural sub-Saharan Africa, and give a little bit of analysis of that. I want to suggest some of the things that I think practitioners in rural water and policymakers in that field need to know about. And I'll highlight one specific current groundwater research initiative, and then towards the end I'll try and give some indications about how we might become better collaborators and communicators. The message is fairly straightforward, that hydrogeology is an applied science, but we could make it a lot more accessible to practitioners and to policymakers and politicians. My focus is going to be on the rural environment, especially in sub-Saharan Africa, and particularly around domestic water and very small-scale agricultural use and water for livelihoods. A little bit of background then. Domestic water supply in the region I'm talking about is very heavily dependent on groundwater. Exactly how much so we don't really know. We can't put numbers on that in many places. What we do know though is that abstractions for domestic use, for rural domestic use, are generally very small. Often less than 1 millimetre per year. Groundwater quality is generally pretty good. There are exceptions which I'll draw attention to. And we know how to develop groundwater. Siting boreholes, designing boreholes, constructing boreholes. We know how to do it. So what's the problem? In the previous version of this presentation, I had a little animal appearing at this point. We have an advertisement on British television which features a meerkat, you know, one of those little South African animals, sticking its head up and saying, "Simples." It should be simple. All these things are in place, but there are a lot of challenges in developing and managing groundwater for domestic water in Africa. And I think we can do a lot better in communicating groundwater science and improving engineering practice. Just a few examples of things that we see as a number of us in this move around countries in sub-Saharan Africa working with rural water. We see hand pumps which are either partially broken or completely broken, sometimes repaired in ingenious ways. If you take hand pumps to pieces, you sometimes find problems like this: severe corrosion of rising mains to the point where no water reaches the surface. We see abandoned boreholes, some of which I'd suggest should never have been commissioned in the first place. It's not a universal situation, but there are too many broken pumps, abandoned boreholes and failing boreholes. There have been a number of studies in recent years, either countrywide or covering large geographic areas, examining the functionality of water points. There are 5 countries represented on this in the data here, showing on the vertical axis functionality. Was the water point working at the time that the survey took place, and plotting it against the age of that water point. And I think what's clear, with one country exception, the green line at the top, we can see that 20 to 25%, even 30% of boreholes, and most of these are boreholes with hand pumps, I should add, 20 to 30% have failed within the first year. And then there's a pretty steady attrition thereafter. If we look globally, truly globally, at the worldwide situation, it is thought that the Millennium Development Goal target for water supply was met 5 years ago, nearly. But still, 750 million people lack access to an improved drinking water source, and nearly half of those are in sub-Saharan Africa. And the situation is particularly bad in the rural parts of sub-Saharan Africa. Of those 44%, about 80 to 85% of those are in rural areas. And if you look at the latest map showing whether countries are on track or not to meet the Millennium Goal target of halving the proportion of people without access to safe water by 2015, using 1990 as the base year, most or many countries in sub-Saharan Africa are not on track, despite the global figure telling a different story. A recent publication by Jean Margat and Jacques van der Gun has tried to pull together some data on groundwater abstractions, country by country, breaking it down, disaggregating groundwater abstractions by sector, irrigation, domestic water and industrial water, and examining each of those as their proportion of total freshwater withdrawals, and adding some indicators to do with renewability of groundwater. As an example here, Morocco, let me just summarize some of the data from Morocco. About 32 million people, extractions of 3 cubic kilometers per year, or thereabouts. More than 80% of that is for irrigation. 47% of the water withdrawn for domestic use comes from groundwater. And over towards the right-hand side, the groundwater development stress, the GDS figure, 40%, groundwater abstractions amount to about 40% of renewable groundwater sources nationwide. Of course, once you get down to basin level, we're talking of a different situation. Recharge, the far right-hand cell of that matrix shows recharge of about 240 cubic meters per person per year. And if you compare that with a domestic water demand, if people are using 100 litres per day, they would require about 40 metre cube per day to put that figure into context. Again, this is the development stress and plotting it across Africa, including North Africa. The groundwater development stress is the ratio of groundwater extractions to renewable groundwater. You can see that that on the vertical axis exceeds 100% in Egypt and Libya, and it's still pretty high across North Africa and parts of the Horn of Africa. But as you move towards the right-hand set of countries, you very quickly get into geographies where the abstractions are less than 10% and progressing to less than 1% of renewable groundwater resources. That doesn't mean that there are not localized problems. I'll come back to that. As far as domestic water use is concerned, the summary tables in that publication can only disaggregate data for 12 countries in Africa, 2 of which are in North Africa, Morocco and Algeria. However, what the remainder do show is that very few countries in sub-Saharan Africa have domestic groundwater abstractions which exceed more than a very small percentage of recharge. The exceptions are in semi-arid and arid regions in North and West and Southern Africa, and almost certainly in the Horn, although of course you can see from the map we don't have data for those, disaggregated data. A little bit on groundwater quality, a couple of maps here, first of all of fluoride, both from IGRAC. Fluoride in groundwater is a fairly widespread problem, particularly in volcanic areas, the Rift Valley and so on. They're not restricted to the East African Rift. Arsenic is actually a little bit more widespread than this map shows, but so far as we know, not too widespread. Iron and manganese, I couldn't find any regional maps showing iron content, for example. We know iron is a big issue in groundwater, but a multi-country study carried out in the late 80s concluded that natural iron content in groundwaters in that region was very low, usually less than 1 milligram per litre, and generally less than a third of that. That's at odds with what we observe, but I'll explain why just momentarily. Outside of West Africa, I find it difficult to generalise about natural iron content. What we do see, though, is that the iron contents in pumped groundwaters, particularly pumped using hand pumps, are often a lot higher, to the point where users reject that water for potable purposes. The vertical axis here is total iron content, iron concentration, with values ranging up to 60 milligrams per litre. And the bottom axis is the duration of pumping starting early in the morning. And what you can see is that as the borehole is purged, the iron content comes right down. And that's a pretty strong clue that the source is corrosion of galvanized pumping components. And that's been well known now for many years, and yet still common practice is to put pumps into boreholes that are made of galvanized iron components, even where pH is low and groundwaters are known to be corrosive. Thermotolerant coliforms, fecal coliforms, microbiological water quality. Just one example here of a study that I supervised in East Africa a few years ago, comparing the thermotolerant coliform counts of a number of different water source categories. The first numerical column there shows the percentage of each of those categories having thermotolerant coliform values of 0, clearly the ideal, and the second column, values falling less than the Uganda national standard for untreated supplies, which is a little bit more realistic. But nevertheless, what you see is even with boreholes, which are supposedly drill blind, cased, and with sanitary seals, we don't see 100% either falling into the 0 category or the less than 50 category. The others fall into various groupings, and depending on how you want to interpret these, I think it's pretty clear that the bottom 3 categories, both covered and open hand-dug wells and open water sources, are problematic from a potability point of view. If you rank those different water source categories and do some more statistical analysis, you see a pattern which is exactly as you would expect, but the key point, I think, is the non-zero values, even for what are supposed to be improved and safe water points. Let me move on. We know very well how to design boreholes from even the first edition of groundwater and wells, and here the second edition, and various more focused, more country-specific or region-specific guidance, more generic guidance. We know very well how to drill and how to design, how to construct boreholes. So where does all this put us? In general, what we can say is that there is enough water for basic domestic and small-scale livelihoods purposes, rural water supply from groundwater. Quality is generally good, with a few exceptions, but we do know how to protect source works from fecal contamination, which is, in most cases, the most important thing. And we know how to design and construct boreholes. But what we see is many groundwater sources failing to give a good service or failing, being abandoned prematurely. And I think, again, those of us who move around Africa and seeing what's going on, we would say that quite a lot of the borehole siting which is carried out is not done intelligently. Designs are often done using standard drawings, which are then not modified on site. Construction is often not supervised at all, or rather inadequately supervised, and that's another reason for which designs are not modified on site. And one of the biggest culprits, I think, is that contracts tend to be of the no water, no pay variety, so that when you combine that with poor supervision, it's the contractor who decides whether the water is there or not, and he wants to be paid. So, as the earlier time series showed, 20-25% or possibly more of boreholes probably should never have been commissioned in the first place, either because of yield problems or water quality issues, and then many of the rest fail to provide good service. I've highlighted there a number of shortcomings in professional practice leading up to the point of delivery of a new water point. If you go beyond that into the post-construction period, why do 3, 4, 5% of boreholes fall out of service every year? Well, ongoing technical and environmental issues to do with water resources, to do with borehole construction, and so on, seasonality. Wider management issues to do with the fact that communities of water users are being expected to manage services that in many cases are unmanageable. And then financial issues to do with the inadequacy of post-construction finance and lack of clarity over who should pay. So you've got the legacy of that poor professional practice, but then inadequate arrangements for management and financing. And all of these problems that I've highlighted seem to me to be symptoms of a number of underlying causes, which include poor appreciation on the part of politicians and decision makers of the importance of groundwater, and poor understanding of how groundwater works, what are the issues to do with groundwater development and management, both by practitioners and politicians, but also by the general public, and especially the water users who are expected to manage groundwater sources. Let me go on to just suggest briefly some of the things that I think practitioners need. The district water officer, who should be standing here, simplified maps which show rock type, lithology, yes, but particularly in relation to different siting approaches, different drilling techniques that are applicable, that show water levels, expected yields, water quality, and so on. Standard hydrogeological maps, such as this one, are fine for people like us, but for many practitioners in the field, something more like that is more helpful. Some very simple text. Just to pick an example at random, not sure about sandstone, maybe better chance of success in valleys. Somewhere else, good aquifer, can drill anywhere, hand dug wells possible. Useful, practical, simple information, but accurate too. What else do practitioners need? They need understanding of groundwater hydrology. How does recharge work? Diffuse recharge, localized recharge. What sort of quantities are we talking about? How do water tables respond to rainfall? And at the end of the rainy season, what does the recession look like and why? Typical seasonal variations which determine when and how deep to drill or dig. What determines through flow in aquifers and yields? In other words, how does the system work? And simple conceptual diagrams like this one are very helpful to practitioners who are not specialist hydrogeologists. A bit more for practitioners of licensed materials. Practical things, siting, how do you do that? Drilling, well construction, supervising contractors, procurement and contract management, costing of boreholes and pricing, monitoring and other subjects. I'll refer again to these in a moment. It needs to be information which is either generic, if that's appropriate, or localized, if that's needed, but very practical, very accessible and readable, and reliable. In other words, how to. If it was the Minister of Finance standing here, what does he need to know, or she need to know about groundwater? Well, certainly a good, clear understanding of the importance of groundwater. I think we had that demonstrated on Monday morning the Minister of Water here. But then you would expect the Minister of Water to understand that. Minister of Finance, maybe not. But its importance as a resource, as a buffer against short-term variability in rainfall and runoff, as a generally good quality resource if it's protected. I think politicians and policymakers need to have some quantitative understanding. How much are we talking about? And what sort of demands are we talking about from the different sectors, from agriculture and industry, from urban and rural domestic water? What's realistic in terms of development ambitions? The importance of groundwater protection. and the importance of long-term monitoring, which a number of speakers so far in this Congress have drawn attention to. How do you convince a Minister of Finance of the importance of groundwater monitoring? He or she will have 50 years of groundwater level monitoring, that's going to cost. But what value does it have for the economy of my country? Can we not do that kind of cost-benefit analysis? So what can we do? I think it starts with what we're good at. We're good at science, we're good at research and development, we're good at publication. But I think what we need to do is to focus more on the needs of developing countries, at least some of us, and on the value of good collaboration and relevant communication between ourselves as specialists and non-specialist practitioners and policymakers. It means involving practitioners and policymakers in the science. It means versioning what we write, not just writing for a high impact factor journal. Yes, do that, but also writing those much simpler, much more accessible publications that our target audiences can use, especially given the fact that we're working often in non-reading cultures. It means working with intermediaries, with other specialists, with knowledge brokers, who I'll mention in a moment, with economists and others, and doing the kind of analyses that matter, not to us, but to non-hydrogeologists. Cost-benefit analysis, for example, is one example of that. I'm going to mention here just one example of a new research program which has been running for about a year and will be moving into a 4-year phase shortly, further 4-year phase. It's called Upgrow, Unlocking the Potential of Groundwater for the Poor. It's a program, it has its own dedicated website. It's a program which is funded by the UK government, but interestingly, the Department for International Development, but together with 2 of the research councils, the ones dealing with the natural environment and the Economic and Social Research Council. It's about $20 million US program, running over 7 years in total, focused on sub-Saharan Africa. And it's about creating the evidence to get good services to the poor. There have been a number of 15 or so so-called catalyst projects which have been running, some of them coming to an end, others running on a little bit longer, on different aspects of groundwater spread across the continent. And shortly there will be an award of 3, 4 or 5 major consortium grants which will begin in early 2015. The big emphasis here is on interdisciplinarity, bringing together the social sciences and the natural sciences, but also research uptake, getting the findings of the research into practice, research into use. This is not easy. I just want to say a few things about interdisciplinarity and research into use. It requires us to get out of our comfort zones and to work with other professions, but also with non-specialists. As far as interdisciplinarity is concerned, we can do it in different ways. Either I do my hydrogeology, you do your social science, we each write a different chapter of a report and we bolt them together. That's not interdisciplinarity. Second option is I do my bit of my hydrogeology, you do your social science, and we together write one report. We bring the yellow and the blue together and create some green. That's getting closer. But maybe the third is too much of an ideal, that we jointly do the hydrogeology and the social science. Similar with research into use. I've heard one of or two people at this Congress so far saying, I'm a scientist, I do my research, I hand it over, it's up to the politicians to make the decisions. And that's one way of doing it, but it's not going to have much impact. An alternative is to plan a research into use strategy from the outset, or going even a step further, undertaking the research, the science, together. An example, a trivial example, is borehole siting. Where should the borehole be located? I think probably most people in this room would say, where there's water. It's obvious. It's not obvious to a social scientist. A social scientist would say, if it's not where people need it, it's not in the right place. And of course, both are correct. In this example, hydrogeology has to take precedence. There's no water, there's no access. But equally, if there's no access from a social point of view, there's no access. A few thoughts about communication. I came across a series of publications not so long ago which present some quite tricky concepts. Economics, macroeconomics, microeconomics, and statistics, would you believe, in comic book form. Cartoony guides to those subjects. I haven't seen one in groundwater yet. Nor have I seen one of the For Dummies series yet for groundwater. I have to confess there's a website where you can create your own cover page, and that's what I did here. Who's going to write groundwater for dummies? It might be needed. But there's a whole lot of other communication techniques that we should perhaps be thinking about. YouTube videos, the water channel uploading videos, massive online open courses, which somebody else at the opening ceremony referred to, and many other options with the information technologies that we have available nowadays. Just a few quick principles if we want to have impact in our science. As Ezekiel refers, he's writing in the context of doing research in communities, but these principles apply much more widely. Engage early with the stakeholders that you eventually want to take up your practices and policies that you may be recommending. Get to know them, build trust, listen and learn. It's all about the relationships that you build up. It's not good enough to stay in our scientific bunkers. We have to get out of them. Use appropriate communication methods, and that probably means a range of communication methods. Get informed consent for what we're doing, whether it's the science or the social science. And once the research project finishes, keep the communication going. I'm sure you'll get access to this presentation, and if you want to follow up the detail of those suggestions, there's a reference point there. Briefly, I want to mention knowledge brokers. It's a new term to me in the last year or so. It seems to me that what they need to be is people with good subject knowledge, but also very high levels of communication and networking skills. They're the people who ask you, the scientists, so what? And then translate those answers into forms which are accessible for practitioners and politicians. One example of a knowledge broker is the Rural Water Supply Network. And I just want to mention here some of the publications that they've been putting out the last few years. The Code of Practice for Cost-Effective Boreholes, a publication on supervising water well drilling, one on siting, one on costing and pricing, one on procurement and contract management, and a more general one on stewardship of groundwater. Very accessible, but still mostly accessible by people in quite a high-level reading culture. And I think even these probably need to be reversioned into simpler forms. So just to conclude, 3 points. I think we would all agree that groundwater is of great importance for the rural poor in sub-Saharan Africa and around the world. We need good science in support of groundwater development, but I think as scientists we need to become much more politically savvy and better communicators if we want to increase our relevance to public policy and practice. Thank you very much.